everyone, and welcome back to the Deep Dive. Today, we're jumping into a really fascinating advancement in video generation, creating movie-quality talking characters directly from, get this, just voice and text. We've got the details in MoCha towards movie-grade talking character synthesis.
That's right. And, traditionally, video generation models have really focused hard on making movement look realistic, but often the expressiveness of the characters, especially when they're talking, kind of got left behind.
Right, or you had other models focusing on just the talking head, which, let's be honest, really limits the body language and how characters can interact.
Exactly. Those models were pretty limited. They couldn't really capture the full picture.
But that's where MoCha comes in. This new work tackles creating talking characters comprehensively. And we mean the whole package. Precise lip sync, genuinely believable emotions, full body actions, and something I find amazing, the ability to have multiple characters actually conversing.
Precisely. The core mission behind MoCha is essentially to, well, democratize cinematic content creation. Imagine being able to generate films just using natural language, with convincing characters who dialogue, express emotions, and perform actions that are perfectly synced with their voice.
That sounds huge. Think about indie filmmakers or smaller studios.
Oh, absolutely. For creators on a budget, this could mean bringing complex character interactions to life without needing expensive motion capture studios or huge animation teams. It fundamentally changes the game for visual storytelling.
And for this deep dive, our main source is that research paper, MoCha, towards movie-grade talking character synthesis. So, to kick things off, what exactly is MoCha?
Okay, so MoCha is billed as the first diffusion transformer model, or DIT, that's trained completely end-to-end specifically to generate these high-quality talking characters.
End-to-end meaning.
Meaning it takes the text and voice directly as input and spits out the video without needing a lot of intermediate steps or complex extra information. Think of it as a more streamlined, efficient process.
Okay, so if you had to pick out the key innovations MoCha brings to the table, what would they be?
Well, first and foremost is that end-to-end training without needing auxiliary conditions. A lot of previous methods needed extra stuff, like reference images of the character or maybe skeletal data, key point.
Right, sort of like guide rails for the model.
Exactly. MoCha, on the other hand, learns directly from the descriptive text and the character's voice. This apparently simplifies the model quite a bit, and they argue it improves the diversity of motion and how well the model generalizes to new things.
Which means it could potentially adapt and improve faster down the line.
That's the idea. It could lead to even more impressive versions quicker.
Cool. What else stands out?
Another major one is what they call the speech-video window attention mechanism. This is all about getting that lip sync really nailed down.
The key part for making speech look believable.
Definitely. This mechanism effectively aligns the voice and the video by using localized temporal conditioning. Basically, imagine the model paying extra close attention to the specific bits of audio relevant to the lip movements happening at that exact moment of the video.
Okay, so it's like zooming in on the sound-to-lip connection second by second.
You got it. It makes the synchronization much tighter, much more believable for anyone watching.
Makes sense. What else?
Then there's the joint speech-text training strategy. This tackles a common problem: the shortage of really large video data sets that also have labeled speech.
Right, finding good data is always a challenge.
So MoCha cleverly uses both video data that has speech and text, and video data that only has text descriptions. For the text-only data, they just replace the speech input with essentially zeros.
Interesting. So it learns from both types.
Yeah, and this helps the model generalize better across diverse actions. Plus, it allows for really versatile control using natural language prompts covering expressions, actions, interactions, even the environment. It's a smart way to leverage different data types to overcome limitations.
That is clever, using what you have effectively. And you mentioned multiple characters earlier.
Yes, that's another big one. They claim MoCha is the first to enable coherent conversations between multiple characters in dynamic, turn-taking dialogues. Previous methods were almost always stuck on a single speaker.
Wow, okay, so breaking that single character barrier is huge for storytelling.
Absolutely. Think about interactive narratives, more dynamic virtual assistants. Having multiple credible characters interacting really opens things up.
Okay, so we have an end-to-end model, super focused on the lip sync with this window attention, smart training using mixed data, and multi-character conversations. So how does MoCha work under the hood? What's the model architecture look like?
All right, so as we mentioned, it uses a DIT architecture. An input RGB video gets encoded into a latent representation using a 3D VAE. Think of that like a highly efficient video compressor.
Kind of boiling the video down to its essence for the AI?
Exactly. It reduces the massive visual data into something more manageable. This latent representation is then turned into a sequence of tokens, like little chunks of information, and fed into the DIT model.
Okay, tokens, like breaking the compressed video into smaller pieces.
Right. Inside each DIT block, there's self-attention applied to these video tokens, basically letting them relate to each other.
Then crucially, there's sequential cross-attention with tokens from the text prompt and tokens from the audio input.
So the video parts are talking to each other and also talking to the text description and the sound.
That's a good way to put it. The audio tokens themselves are extracted from the raw sound waves using a model called Wave2Vec2, and they're processed to match the dimensionality of the latent video tokens.
So everything lines up dimension-wise. And for the actual learning process, MoCha uses something called flow matching as its training objective. It's an efficient way to simulate continuous time dynamics, basically how things change smoothly over time.
Got it. Let's go back to that lip sync part. Can you break down that speech-video window attention a bit more? You said it was key.
Sure. So like we touched on, older models for talking heads often use 2D diffusion models. They generate video frames, kind of one after another, auto-regressively.
So frame by frame.
Right, and they'd be conditioned on the audio tokens that corresponded just to that specific frame. That helped ensure synchronization because the audio for this frame guided the generation of this frame.
Made sense. Little bit of audio, little bit of video generation.
But with DIT architectures, two key differences make that kind of direct alignment tricky. First is temporal compression from the 3D VAE. The video gets compressed in time, say, T frames become TR tokens, where R might be 4 or 8. But the audio often keeps its original temporal resolution, T.
So the video tokens are sort of running at a faster, more compressed timescale than the audio tokens.
Exactly, which can mess up fine-grained lip sync if you're not careful. The second difference is parallel generation. Unlike the frame-by-frame models, the DIT generates all the latent frames at the same time, in parallel.
Okay, not one after another.
Right. So if you just use simple cross-attention, any video token could potentially pay attention to any audio token, even ones from way earlier or later in the speech.
Which would lead to mismatches, lips moving based on sound from the wrong moment.
Precisely. So the speech-video window attention restricts the attention. Each video token is only allowed to attend to a limited time window of audio tokens specifically, the ones covering the corresponding original frames, plus maybe one token on each side for context.
So it forces the model to only look at the relevant nearby audio.
You got it. Ensures local context and continuity, significantly improving that lip sync. It's a pretty logical fix when you think about the parallel generation problem.
Seems very logical. Okay, now, how about generating those multi-character conversations? How does MoCha keep everything straight?
Well, interestingly, MoCha generates videos with multiple clips simultaneously, using the same basic architecture as for single clips. There's nothing fundamentally different added, just for multiple characters.
So how does it maintain consistency, like the same character looking the same across different shots?
That comes down to the self-attention between the video tokens across all the clips being generated together. This mechanism ensures that characters and the background environment remain consistent. It's like the model remembers this is person A across different segments.
Okay, so the self-attention handles keeping the characters and scene consistent.
Right. And they make an assumption. Only one character speaks at a time. So the changes in speaker detected in the audio signal itself actually guide the model on when to transition between clips or characters.
So it uses the audio turn-taking to know when to switch focus. No extra signal needed.
Seems like it. Pretty efficient. And to guide the model on who is doing what in the prompt, they use a structured prompt template with character tags.
How does that work?
You first specify the number of clips. Then you introduce each character with their description and a unique tag, like character 1, character 2. Then, when describing each clip's action, you just use those tags.
So instead of describing the woman with the red hat every time,
You just say character 1 is speaking, or character 2 gestures. It makes the prompts much clearer, concise, and consistent, especially for complex scenes with lots of back and forth. Seems like a very organized way to instruct the model.
definitely sounds more manageable than free-form text for complex interactions. Okay, let's dig a bit more into the training strategy. You mentioned that joint speech and text approach.
Yeah, the training setup is quite layered. As we said, to deal with limited speech-labeled video data, they train jointly on ST2V, speech plus text-to-video, and T2V, text-to-video data. About 80% of the training uses the ST2V data, where the model learns the full connection.
And the other 20% is the text-only video?
Right, where the speech condition is zeroed out. For the listener, this means the model learns from a wider variety of information sources, making it more adaptable.
And what's the main benefit of adding that text-only data?
It primarily improves the model's robustness and its ability to generalize to a wider range of visual actions and scenes, even those without a specific voice track during training. And importantly, after training, it allows the model to generate video driven only by text prompts, which is really useful.
Ah, so it gives it a broader visual grounding beyond just speech-driven actions.
Exactly. And on top of this joint training, they use a multi-stage human video learning framework. They notice that the influence of speech is strongest for low-level movements like lips and facial expressions.
Which makes sense. They're directly tied to the sound.
But it gets weaker for higher-level movements like gestures or full-body actions, which are also just harder to generate accurately. A hand wave might depend more on the overall context than the specific word being said, right?
Absolutely. So how does the multi-stage part work?
They structure the training in stages. They start by training mainly on close-up shots, where that speech-video correlation is highest. In each subsequent stage, they reduce the amount of data from the previous stage, say by 50%, and introduce harder tasks with less direct speech influence, like medium shots.
So gradually increasing the difficulty and complexity.
Precisely. And crucially, in stage 0, before introducing speech signals at all, they pre-train MoCha exclusively on text-conditioned video data. This builds a solid visual foundation before layering on the complexities of speech synthesis.
So it's like building the model skills from simple visual understanding up to complex speech-driven performance.
That's a great way to put it. Now, to actually test how well MoCha performs, the researchers created a specific benchmark called MoCha Bench. What can you tell us about that?
Right, MoCha Bench. It's basically a custom test set designed specifically for this task of generating talking characters. It includes 150 diverse examples, each with a text prompt and a corresponding audio clip.
Covering different scenarios.
Yeah, they included close-ups, medium shots, various character activities, different emotions, and even different character facings. And an interesting detail is they used Llama 3 to enrich the text prompts, making them more descriptive and varied.
Okay, and how did they compare MoCha against other existing methods?
They compared it with several established audio-driven talking face methods, like Sad Talker, Annie Portrait, and Halo 3. Now, these typically need a reference image to start.
Right, they animate an existing photo.
Exactly. So for a fair comparison, they provided these models with the first frame generated by MoCha itself.
Ah, okay, so starting from the same visual base. Smart. What were the results like?
The qualitative results, just looking at the videos, were apparently quite striking. MoCha showed well-synchronized lip movements, natural facial expressions, and realistic body actions that matched the text prompts.
And the competitors?
The comparison methods reportedly showed limitations, things like stiff head movements, inaccurate lip sync, sometimes jerky articulation, and visual artifacts. You know, the usual uncanny valley stuff we sometimes see.
Yeah, getting that naturalness is the hard part. What about quantitative metrics, numbers?
They used automatic metrics specifically designed to measure lip sync quality, and MoCha came out on top there, confirming the visual observations.
Okay, metrics look good. But at the end of the day, human perception is what really matters for this kind of output. Did they do human evaluations?
They did. They ran comprehensive human evaluations across 5 key areas: lip sync quality, facial expression naturalness, action naturalness, text alignment, and overall visual quality.
And the verdict. MoCha significantly outperformed all the competitors on all aspects. Its average scores were close to 4 out of 5, where 5 represented indistinguishable from real video or movie production quality.
Wow, close to a 4 out of 5. That's really high praise from human evaluators.
It really is. And interestingly, methods like Sad Talker and Annie Portrait consistently scored around 1 for action naturalness, which makes sense, as they basically only do head movements. And text alignment wasn't applied to them since they don't take text input.
So humans found MoCha almost movie quality across the board. That's impressive.
Definitely a strong showing. And to really understand why MoCha works so well, they also performed ablation studies.
Right, where they basically switch off specific parts of the model to see how much performance drops.
Exactly. It helps isolate the contribution of each component. For instance, when they disabled that speech video window attention mechanism, they saw a noticeable decrease in lip sync quality, confirming its importance.
Makes sense. What else did they test?
They also tried training MoCha only with the ST2V data, without the joint T2V data. When it did that, they observed a degradation in generalization ability, demonstrating the benefit of the diverse data brought in by the joint training strategy.
So those studies really nail down that both the window attention and the joint training are critical pieces.
Seems so. They validated their core design choices. And what was the paper's main conclusion from all this?
The researchers conclude that MoCha sets a new standard for AI-driven talking character generation. They emphasize its superior realism, expressiveness, controllability, and generalization compared to prior work. They see it as a significant step towards automated cinematic storytelling.
So we've taken a fascinating look at how MoCha is really pushing the boundaries in video synthesis, enabling these movie-grade talking characters from just voice and text. Its ability to nail lip sync, generate realistic emotions, full actions, and even multi-character conversations just opens up so many possibilities for content creation.
Absolutely. The implications are pretty vast. It's not just about potentially transforming film and animation production, though. That's huge. Think about digital assistants, virtual avatars, advertising, educational content.
Right, the ability to control the expressiveness and actions of digital characters using natural language, that's a massive leap forward.
Which brings us to a question for everyone listening to ponder. What kinds of stories or applications do you think will become possible with technologies like MoCha in the near future? How might this change the way we create and maybe even consume audiovisual content?
Definitely a field with an exciting future and lots of questions still to explore.
We hope you found this deep dive as fascinating as we did. Until next time. And before we sign off, remember to keep exploring topics in machine learning and artificial intelligence. We invite you to subscribe to the AI and Data Insights newsletter and follow us on LinkedIn and X.